So in this section here, we talk about power series. Power series, so it's a special looking series. I will give the definition first to show you what a power series is. Power series, obviously, the name indicates some kind of a power function, right? A power series is a series of the following form. The summation sign. So all the terms, they are all some kind of a power function. Let's think about the power function. There is some constant in the front. There is this x term minus some number and raised to the power of n. N can start from 0. So when n is 0, this part is just a constant 1. So we're looking at a constant. And the power here keeps increasing from 1 to 2 and to infinity. So this is how a power series look like. We can plug in different n's here and write this apart so you have a better picture of what this actually is. n is 0, you're looking at a constant that we call C naught. n equal to 1, so that's another coefficient to the power of 1. So this is a linear function or power function of a degree 1. C2 x minus a squared. Now I can see the pattern. So each term, there is always this coefficient in the front, and each term, they all look like x minus a raised to some power, and this power keeps rising. So that's the power series. So this number a, okay, this number a that we call x equal to a, okay, this number a, we call this the center of the power series. The center of the power series. C sub n, the C sub n, I guess we can call these the coefficients. So in general, the C sub n's or all those coefficients, they're all given. A will also be given, so A could be a number like 1 or 2. So these are all given quantities. The only thing that's changing is x. The standard question in this section is this, okay? So this is a standard question. Actually, almost all questions look like this. For what values of x? So what are the x values that'll make this power series converge? For what values of x the power series converge? So that's the almost the only question we're trying to figure out in this section here. What are the x values that'll make this power series converge? Because x is the variable here. And I can plug in any x that I want. So to make some sense about the question we're raising here, let's make a quick observation. For example, you can plug in x equal to a. Let's see what happened at a. When x equal to a, these terms, they're all zeros. So the power series becomes this. C naught C1 times by, because we're plugging x equal to a, okay, we're plugging x equal to a. It's 0, C2 0, and so on. So these are all its zeros. So the power series obviously converge because it's really just a constant. We can also kind of picture that if x is close to a, if x is a number that's really close to a, so those terms will be small. And the power series will have a better chance to be a finite number or converge. If x is far away from a, which makes this term big, then there is a chance this guy will be divergent. So if x is close to a, I would say better chance to converge. In other words, better chance to be a finite number. If x is far away, so all those power functions back there, all those power terms, they will become bigger. Less chance to be convergent. I hope that makes sense. So this is what intuition tells us. But exactly how do we solve this problem? Now I will show you how this is done. Okay, now I will show you how this is done. What we need in this section is the ratio test. Okay, the ratio test. I want you to pause here for a minute and look up the ratio test real quick. Okay, look up the ratio test real quick. So I start with a concrete example here. So what are the x values that make this power series converge? And the power series look like this. Does this guy converge? So that's the question. And also notice, because we have n on the denominator here, so n cannot start from 0. That's why I say we pick n goes from 1. Okay, goes from 1, because otherwise this guy is undefined. So how do we answer this question? What kind of x will make this guy converge? So now that we have all sorts of tests, but the most recent one that we learned is the ratio and root test, which can be applied to a series that's not necessarily positive. Okay, ratio and root test can be applied to a series that's not necessarily positive. So to apply the ratio test, we're gonna call this whole thing a sub n. So the power series becomes, sigma a sub n, where a sub n is this big chunk. Okay. So here's the standard start of the solution to this type of problem. Okay, it's pretty standard, so you may want to memorize this. Okay, you may want to memorize this. The standard start is to let a sub n to be this whole chunk, and I rewrite it into this form. Okay, so that's my a sub n. So let's recall the ratio test. The ratio test says you need to calculate the limit of this ratio. So this is something you want to memorize. Okay, folks? Do you remember that? Let n goes to infinity. Ratio test says whenever this number turns out to be something less than 1, the series converge absolutely. Bigger than 1, diverges. Equal to 1, the ratio test fails. Okay? So that's the criteria we're going to use. But let's take a look what this guy is. There is a big absolute value sign here. We have a sub n plus 1, which is just replaced in here with n plus 1. Divide by a sub n, multiply with its reciprocal. Okay? So let's simplify this, okay? Let's simplify this. Here we have n over n plus 1. I can take this outside because this guy is always positive, so I don't need the absolute value sign here. Followed by x minus 3, and I do need the absolute value sign here. And we calculate the limit of this when n goes to infinity. I mean, this term obviously does not depend on n. There's no n in there. So just figure out the limit of this thing here, which is clearly 1. Okay, this part goes to 1. So the limit of the ratio is x minus 3. In other words, this limit depends on x. Okay, this limit depends on x. The limit of this ratio depends on x. So now we can recall the ratio test. By ratio test, the power series converges absolutely. Absolutely means what? Absolutely means even if you take the absolute value of all the terms, that positive series still converge. By ratio test, the series converges absolutely, and parenthesis, therefore convergent. Okay. Any series that converges absolutely must converge. Okay. Therefore convergent. If this ratio that you calculated is less than 1. And it diverges if this number you calculate is bigger than 1. And that's the end of the story. What happens when this term equal to 1? And that's something requires some separate study, okay? Separate study. But now let's take a look. What kind of x are we exactly looking at here? What does that mean? And what does that mean? So what kind of x are we looking at? So I'd like to figure out the solution to this inequality here. Let's try to solve this absolute value inequality. Some numbers absolute value is less than 1 is equivalent to say that number is between some number absolute value is less than 1, meaning that number is between -1 and 1. So this gets rid of the absolute value sign and becomes the usual inequality here. To get the precise answer, we add 1 to each component. Not add 1. Actually, we need to add 3 because I need an x in the middle. So add 3, add 3, add 3. So that gives you a precise interval, okay? Precise interval. So on this interval, the series converge, right? Converge. Actually converge absolutely, but converge. So that is that interval. Outside, okay, bigger than 1 meaning, I guess means x will be bigger than 4 and less than 2. So I know for sure this is the interval where the series converge, right? Converge. But we're not so sure what happens if this equal to 1. So obviously this equal to 1, meaning either x equal to 2 or x equal to 4. For those two cases, when x is 2 or 4, the limit of this ratio turns out to be 1. And I can't apply ratio test. Ratio test fails. But I have to take a closer look at those points. So at those two endpoints, I always have to plug them in. Okay, let's plug them in. That was x minus 3. Now x is 2. So when x is 2, that's what the series is, which is just sigma 1 over n. Well, that's actually not true because 2 minus 3 is what? Negative 1. So actually it's not 1 to the power. It's not 1 on the top. Instead, it is negative 1 to the power of n. Yes? I cannot directly apply ratio test, but this is clearly an alternating series. Alternating series. And let's try to recall alternating series test. And we know this guy actually converges by alternating series test. For those who remember alternating series test, it was a test that can be easily applied, where you have to look at the positive part, which is 1 over n. You want to see whether this guy decreases. Yes, 1 over n clearly decreases, right? It gets smaller and smaller. And moreover, it has to go to 0, decrease to 0. So that's alternating series test. When x equal to 4, okay, you plug in 4 there. So I want you to verify that this is the same as sigma 1 over n. That's the actual series at x equal to 4. As we all know, this guy actually diverges. Okay, diverges. Diverges. So we look at the endpoint separately, and in the end, the final answer to this problem is this. Okay, hence we're looking for where the series converge, right? Converges on this interval. Okay, from 2 to 4. At 2, it actually converges, so I use brackets here. At 4, it does not converge because sigma 1 over n divergent. So that is the actual interval on which this guy converged. And I can plot it. There's a 2 here, there's a 4. At 2 converges, everywhere inside also converges except at 4. Alright? So that was, later we're going to call this interval of convergence, okay? Interval of convergence. So what we notice in this example here is the series converges on some kind of a interval. And the interval is from 2 to 4. Notice the center, the so-called center of the power series is 3, which happens to be right in the middle of the so-called interval of convergence. And that turns out to be not a coincidence. Turns out we have results on interval of convergence. So this theorem provides different scenarios on which the power series can be convergent. So that's a standard form for any power series. Any power series, one of the following must hold. Number 1, the power series may converge only at a single point, only at x equal to a. Everywhere else it diverges. As I showed you earlier, that when x equal to a, this can indeed always converge because you are looking at a lot of zeros back there. Number 2, and this is the scenario we see from the previous example, converges on some interval x minus a less than some constant, and diverges outside. Here's our previous example. This guy converges if x minus 3 less than 1. Okay, so the R in this example is 1. You see this guy? R is 1. So if that's the case, R obviously measures the size of the interval, measures how big the interval is. So we call this radius of convergence. So this is just a concept really, okay? And this concept is somewhat important. So you need to know what radius of convergence means. So R is called the radius of convergence. The previous example, if you can pause for a minute and look back, the radius convergence was 1. Converges only a single point, converges on some open interval. Finally, it converges for all x. That turns out to be possible as well. For all x. So in this case, I guess we can call the radius of convergence is what? If it converges for all x for all real numbers, in this case, we say the radius is infinity. Okay, we say the radius of convergence, or is infinity. So 3 scenarios: converges single point, converges some interval, and converges for all x. Finally, let's mention about the interval of convergence. The interval on which the series converges is called interval of convergence. Okay, we already did this in the previous example where we found out where this guy converges. That interval is called interval of convergence. And we want to remind you, you must always consider the endpoints. Okay, must also consider the endpoints, because that's where the power series or the ratio test or root test fails. So you must also consider the endpoints separately. Okay, separately. Take a closer look. So now I will show you an additional example. Okay, I will show you guys an additional example. Find out the radius of convergence and interval of convergence of the following power series. Here you have a power function here. 6 is the so-called center over this coefficients. So in most cases, we can solve this interval convergence problem for power series. Use the ratio test. Okay, use ratio test because it's easy to calculate the ratio of those two terms. But sometimes you can also do the root test. Okay, I'm going to try to do the root test to this problem. So let this whole thing to be the term in any series. So let a sub n to be this whole piece. Then let's record the root test. Root test, we need to calculate the nth root of the absolute value of this. And let n goes to infinity. And that's how root test looks like, right? Whenever this guy less than 1, converges absolutely, bigger than 1 diverges, equal to 1 inconclusive. So here we're looking at the nth root of, x minus 6 absolute value, because we're taking absolute value to the power of n, over n to the power of n. So now you can see it's not a bad idea to take the nth root, because that'll get rid of all those power n here. And when you simplify this whole thing here, the top is x minus 6 absolute value. Take the nth root of the bottom, it's just n. Alright, I want you guys to verify this independently. Now let's find out what is the limit. What happens when n goes to infinity? Well, whatever x is, the top is always a final number. N goes to infinity. So this is always what? Turns out this is always 0. Does not matter what your x is. And that's always less than 1. What does that mean? That means this power series, the power series, converges for what kind of x? It's always less than 1. Does not matter what your x is. That's why we say the power series converges for all x. Okay, for all x. And the so-called radius of convergence, R will be what? Infinity, okay? Radius convergence is infinity because it's for all x. So that wasn't this is a perfect example for power series that converges everywhere. For all real number x. And now we'll show you an example that converges only at a single point. Remember that theorem? This theorem says there are only 3 cases. Either converge a single point, converges for all x, or actually this is the most cases, it converges on some interval, converges for some x. I showed you an example for this, and I showed you the first example was this guy, and now I will show you this scenario. Converges only at a single point. N factorial, alright, I guess that is the coefficient. N factorial, as we know, this guy can get really big real quick. Here's the power function. And I want to remind you, this is not in that standard looking form. The standard looking form was this. Some constant c sub n, x minus like a coefficient, minus some center to the power of n. So that does not look exactly like this. But nonetheless, this is still a power series. Okay, nonetheless, this is still a power series. If you want, you can actually somehow convert this or transform into this form. Okay, into this form. But does not really matter. Okay, does not really matter. The question is always the same. Find out what x make this guy converge. So standard procedure, we try to apply the ratio test. So that was the thing that popped up in the ratio test. Absolute value sign, a sub n. A sub n refers to this whole thing here. So a sub n plus 1 is n plus 1 factorial 2x plus 1 to the power of n plus 1. N factorial to the power of n. Alright? So let's try to simplify this. Limit n plus 1 factorial, n factorial. Many of us can see this is actually just n plus 1. Back there, this is power n plus 1, and this is power n. So you get the absolute value of 2x plus 1. So what is the limit of this thing that we just simplified? N goes to infinity. And this is 2x plus 1. Some of you may say, wait a second, this is always going to be infinity. Notice this will be indeed infinity unless this term is 0. If this is a big 0 back there, this is always a 0. Okay? So here's the limit. If x is negative 1/2, okay? If x is negative 1/2, this term is always 0, and n plus 1 times by 0 is always a 0. So the limit is always 0. Anything that does not make this guy equal to 0, the limit becomes what? Infinity. Ratio test says whenever the limit of ratio is less than 1, converges. Bigger than 1, diverges. And that's how we come to the conclusion that this power series converges only when x is this number here, okay? Alright, now here is the last example in this section that summarizes all the detail that we've discussed so far, okay? And it goes like this. Last example. Find the radius. And interval of convergence. Alright. So here n starts from 1, okay, and that's okay. Because n equal to 0, it's just the first term will be 0. We are looking for radius and the precise interval of convergence for this problem. Apply a ratio test. Meaning we have to calculate the limit of the ratio. So this is something you guys need to memorize, okay? A lot of you oftentimes have problem starting a question like this. Memorize this, okay? Memorize this. That's how the ratio test goes. The limit of the ratio. Big absolute value sign. A sub n once again refers to this whole piece here. And I will put it down here. That's A sub n. The top, replace the n with n plus 1. And it's not too hard to simplify this. Here's what I found. N plus 1 over n. So basically flip this guy over, okay? Multiply with its reciprocal. That's what it is. 2 to the n on the top over 2 to the n plus 1. So we're trying to associate the similar terms. For those two guys, we can obviously cross off x minus 3 to the n. So we just have x minus 3 with the absolute value sign. Okay. This one goes to 1, and that is just 1/2. So in a 10 points in a 15 points problem, if this is a 15 points problem, calculus ratio, it's probably like 5 points. And then once again, whenever less than 1 converges, bigger than 1 diverges. The series converges whenever this is less than 1. But now we're looking for interval of convergence, so I need somehow to solve this. Okay, we need to solve this. So let's try to solve this. Multiply on both sides by 2. That's equivalent to this. So x minus 3 is betraying the absolute value is less than 2, meaning this number is betraying negative 2 and 2. Add 3, add 3, add 3. So that's the interval. But once again, we have to talk about the endpoints. Outside of this interval, okay, meaning x is less than 1 and x bigger than 5, that's always divergent. Always divergent. But x at those two endpoints, we're not so sure. So always check for the endpoints for x equal to 1. What does that mean? That means we need to plug that in. Plug in x equal to 1. Okay, plug in x equal to 1 here. The series becomes this. I'm going to plug in x equal to 1. That's 1 minus 3, which is negative 2, to the n. So what do we know about this? Let's take a look. Negative 2 to the n is the same as negative 1 to the n and then 2 to the n, because negative 2 is negative 1 times by 2. So those two terms crossed off, you are looking at something like this. There's a negative 1 to the n here. There's this n back there. I know this is an alternating series. This is alternating series, but the positive part does not appear to go down to 0. Okay, the positive part does not appear to go down to 0. So this guy won't be convergent. Okay, indeed, we can find out this guy actually diverges, which diverges by the fact that this whole thing here, okay, this whole thing does not go to 0, and that's the test of divergence. Okay, which diverges. You have to think about the test. Okay, is the test of divergence. Let me remind you the test of divergence, which was the first step we talked about at the very beginning of this chapter. Test of divergence says for any series that look like this, it doesn't matter whether this guy is positive or negative, as long as a sub n does not go to 0, It diverges, okay? As long as a sub n does not go to 0. You see this guy right here? I don't care whether it goes to 1 or 3 or infinity or does not exist. It does not go to 0. Diverges. The second point is at x equal to 5. I want to find out what happened there. So you plug in 5 there, you get 2 to the power of n, which is actually just sigma what? Sigma n, okay? This is obviously diverges, okay? Which clearly diverges. Diverges as well. So for this example, at the two endpoints, the series both diverges. So the final conclusion is this. This is a very important example. Okay, you will definitely see this on your final test. So the interval of convergence is from 1 to 5, not including 1, not including 5 either. There was another piece that we wanna answer. That is, what's the radius? Okay, what's the radius? Now, what's the radius? So you look at this interval from 1 to 5. From 1 to 5. The whole size is obviously 4. Cut this in half will give you the radius. Okay, so it's a simple algebra problem. Thus, the radius of convergence measures how big this interval is. Okay, the radius convergence is not 4, okay, 2. Cut this guy in half. From 1 to 5, that's 4. Okay, cut this guy in half, that's radius, which is 2. Alright? And that ends power series, okay? Ends power series. So basically, power series, to study the power series is really application of what? Ratio test or sometimes root test. But for most problems, we should be able to take care of it with the ratio test, okay, with the ratio test.